This video is for the Stoichimetry worksheet on Moodle. By watching this video, you should be able to complete the worksheet on Moodle and submit for grading. Stoichiometry is study of the quantitative relationship for a chemical reaction. So basically what it means using a balanced chemical equation and relate the quantity of one substance to another substance in a chemical reaction. To do stoichiometry, as we use counting terms to describe the specific quantities of different things in life, in chemistry we will use mole. Mole is the base unit for quantity in chemistry in SI system. 1 mole of a substance contains exactly 6.022 times 10 to the power of 23 elementary quantities of that substance. This number is known as Avogadro's number, and this number is a constant for a mole. A mole of any substance contains 6.02 times 10 to the power of 23 elementary particles of that substance, and 6.02 times 10 to the power of 23 known as Avogadro's number. Here we are looking at 3 different elements, and elementary particles of the elements are atoms. So if we have 1 mole of carbon, we will have 6.02 times 10 to the power of 23 carbon atoms. If we have 1 mole of sodium, we have 6.02 times 10 to the power of 23 sodium atoms. If we have 1 mole of gold, then we have Avogadro's number of gold atoms. Now, if we end up having more than 1 mole, then that factor will be multiplied by this number. As it was said earlier, a mole represents the quantity of a substance, and 1 mole of a substance contains Avogadro's number of elementary particles of that substance. When we look at the molecular compound, 1 mole of molecular compound like carbon dioxide has 6.02 times 10 to the power of 23 molecules, because molecules are elementary particles of a molecular compound. When we talk about ionic substances, when we say 1 mole of an ionic substance, that 1 mole of ionic substance has 6.02 times 10 to the power of 23 formula units of that substance. As you see in this table, aluminum is an element, then 1 mole of aluminum will contain Avogadro's number of aluminum atoms. 1 mole of sulfur, which is an element, contains this many Avogadro's number of sulfur atoms. 1 mole of water, which is a compound, molecular compound, contains 6.02 times 10 to the power of 23 molecules of water. 1 mole of vitamin C, which is a molecular substance, contains 6.02 times 10 to the power of 23 molecules of vitamin C. 1 mole of sodium chloride, which is an ionic substance, contains Avogadro's number 6.02 times 10 to the power of 23 formula units of sodium chloride. So far we should have learned that 1 mole of any substance is equal to Avogadro's numbers of elementary particles of that substance. Therefore, we can come up with this equality that 1 mole is always equal to 6.02 times 10 to the power of 23 particles of that substance. We learned about equality in chapter 1. Now we can use the equality between a mole and Avogadro's number to set up conversion factors like they are shown in here based on this equality. Now, since we know what 1 mole is, we're going to use that knowledge to write a plan to convert moles to atoms or molecules, use Avogadro's number to write conversion factors, set up the problem to calculate the number of particles. In this problem, we are trying to find the number of carbon atoms in 0.50 mole of copper. As you can see, if it was 1 mole, then we knew how many copper atoms we would have had, which would have been 6.02 times 10 to the power of 23. But we do not have a mole, we have half a mole. To find a half a mole, in this problem, we are going to be finding the number of copper atoms in 0.5 mole of copper. What we know that 1 mole of copper has Avogadro's number of copper atoms, but the given amount is not 1 mole, it's 0.5 mole. Since we know 1 mole of copper contains Avogadro's number of copper atoms, we can set up a conversion factor as is shown in here. Then we set up a problem like we did in chapter 1 using dimensional analysis. We always start with the given amount, which in this case is 0.50 mole of copper, and we want to get rid of the mole, and we want to come up our answer to be in atoms. Therefore, that's how you would set up the conversion factor. So the mole of copper would cancel out, and then you will get 3.0 times 10 to the power of 23 copper atoms. This problem is exact opposite of the previous problem. In this problem, we are given the number of molecules, and we are trying to find the number of moles of carbon dioxide. To do this problem, we will be using Avogadro's number again, because we know 1 mole of carbon dioxide contains 6.02 times 10 to the power of 23 molecules of carbon dioxide. So in this problem, the given quantity is the number of molecules of carbon dioxide. What is needed is the moles of carbon dioxide. And like I said in the previous slide, 1 mole contains Avogadro's number of molecules of carbon dioxide. So we are going to use our equality. 1 mole is equal to 6.02 times 10 to the power of 23 carbon dioxide molecules. Set up a conversion factor, then start doing the problem. And like I mentioned in previous slide, you always start with the given substance. So in this problem, we're going to start with the number of molecules, and we need to set up the conversion factor based on this equality, so we can get rid of the molecules. Therefore, the molecules goes into numerator as is shown in here, so they can cancel out. A molecular formula can represent 1 molecule, or it can represent 1 mole of a substance. If we are looking at the substance at the molecular level, then if we have 1 molecule, we can say we have 6 atoms of carbon in glucose, 12 atoms of hydrogen, and 6 atoms of oxygen. But if we say we have 1 mole of glucose, then it means we have 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen. So if we are given the molecular formula of a compound, we can always say how many moles of each atom we have in the compound. Like in this case, for aspirin, if we have 1 mole of aspirin, we can say we have 9 moles of carbon atoms in every 1 mole of aspirin, 8 moles of hydrogen in every 1 mole of aspirin, 4 moles of oxygen in every 1 mole of aspirin, or we can say for 1 mole of aspirin we have 9 moles of carbon, 1 mole of aspirin we have 8 moles of hydrogen, in 1 mole of aspirin we have 4 moles of oxygen. In the next slide, we are going to learn how to relate 1 mole of a substance to number of moles of different atoms, or different number of moles of a substance to a different number of moles of atoms in the substance. In this problem, we want to find the number of carbon atoms in this problem, we are trying to find the number of moles of carbon in 2.3 moles of this compound, which is known as propyl acetate. So the first thing we need to find out is that how many moles of carbon we have in every 1 mole of the compound. When we looked at the chemical formula of the compound, we find out that for every 1 mole of the compound, we have 5 moles of carbon. Therefore, we can use this equality to set up conversion factor like it is shown in here. Like in the previous problems, we always start with the given amount, which is 2.3 moles of this compound, propyl acetate. Then we multiply that by a conversion factor that we have set up in here. And the reason that we use this one is because we want to get rid of the number of moles in here and there. The molar mass of an element is the mass of 1 mole of that element. You get that information from the periodic table. So if you go to periodic table, you will find that 1 mole of silver has a mass of 107.9 grams. 1 mole of carbon has a mass of 12.01 gram, and 1 mole of sulfur has a mass of 32.07 grams. So the molar mass of the elements are found in the periodic table in different rows and different columns. In the next few slides, we learn how to find the molar mass of a compound. In this slide, we have a compound that is known as calcium chloride. And to find the molar mass of calcium chloride, we need to find out how many of each elements we have in the compound. So when we look at the calcium chloride, we find out that we have 1 calcium and 2 chlorine atoms in the compound. And the mass of calcium is 40, for each one is 40.0 grams for calcium,